Welcome everyone. This is the first talk of the Industrial Connect program of IEEE IISc VLSI Chapter. And we are very grateful to Dr. Veena for giving this talk on SOC solution. So Dr. Veena is a Bangalore-based technologist, system-on-chip architect, and educator, currently working as staff instructor in Synopsys. She has a career spanning over 3 decades and has formed various VLSI design and incubation centers. She has co-founded Sense Semi Technology Private Limited, a healthcare company. She was the research head and adjunct professor in the Department of Electronics and Communication Engineering, BNM Institution of Technology, Bangalore. And she has executive management degree from IIM Bangalore. She has filed 5 patents for SenseMe and 2 for BNMIT in VLSI and healthcare domains. She is the author of the books A Practical Approach to VLSI System on Chip Design, 2nd edition, and SOC Physical Design, authored by Dr. Shivanand Koteshwar, both published in 2022, and IoT and M2M Communication Technologies, published in 2021. She is also a senior IEEE member. So, with a huge round of applause, please welcome Dr. Veena.
So, good morning, everyone. It's really a pleasure to be talking to you all. I'm here to talk to you on the paradigm shift which is happening from system on chip to solutions in totality. Actually, traditionally, we have been working on SOC design by integrating processors, DSPs, memories, individual subsystems. And but the paradigm shift which we are seeing today is designing them or developing them in total, that is as a solution itself, so that the advantage you get in a solution approach is basically you will get the designers or the developers will have a complete freedom to optimize and energy efficient and high performance solutions which is tailor made to a particular application or the use case. So why it is so? Let us see why it has happened. And another thing is the system complexity, which is driving this, and sophisticated applications, which is the prime driver for this paradigm shift. So let's see if that is true. And if you all agree, by end of my talk, I think we are on the right track. I am on the right track, I would say. Yeah. So I'll just set, I'm not here to talk more technical into the solutions or the system design aspect, because you're in the best place here to do that, to solve technology problems. Okay. My thing would be to really share the experiences in totality and the trends which is happening around us, and then see what are the takeaways as a developers, as a aspirant VLSI designers, what we get out of this. Let's see how it goes. So can you identify what are these? Huh? Okay. Any others? Any other guesses? From online viewers?
Pen with camera, multi-purpose.
What is it?
Pen with camera.
What is it? Right, it is a laptop system, just in a cap, probably carrying this. Okay. Yeah. Am I audible now?
Yes, ma'am.
Yes, ma'am.
Yes.
Fun? Various places. You? All right. So this was the second quiz. I was trying to show you a product, and this appears to be a keyboard projector, which you can use it on any planar screen, okay, to project it. So that is another thing. I'm just giving you ideas of various products. So guess what is this? Projector. Let's see what is it. Yeah. It's just a phone-like thing. We just have a projector on keyboard and all. Typically, the gadgets which we carry, like smartphones and all, come with a very small keyboards, right? For many of, especially the elderly people, they find it hard to really use the keypad on the device. So this, you can use it to project a full-fledged keypad on the planar surface, and then you can use it as a keyboard. So yeah, we are seeing this trend, like everything around us is becoming smart and really more user-friendly. and it is more adaptive to the requirement of a use cases, right? I mean, various use cases. And we are seeing the development of flying cars. You can see a humanoid, which is really a couple of years back, we felt that machines can't feel, right? Today we have the machine which can really gives you a complete kind of a support system for you, right? You have a humanoid, AI-based humanoid, and you have flying cars, drone kind of a thing which can do really traverse in a very difficult terrains. And then what is this? Can you guess what is this? Can you guess the last quadrant device, online viewers? It's a bathtub, okay, which will give you a spa kind of feeling and the complete, very fancy bathing this support system. Yeah, and we also have developments in the area of electronics where we have foldable gadgets, right? Which is coming, you can see it in the near future. And we see all kind of artificial intelligence based products. And you can even see the body scanners, right? You can scan all your, I mean, your breath analysis. It can do all medical analysis with a simple gadget in hand. You have flying cars, you have paying system. Can you imagine this can be a paying system? The ring, which will just can scan it to pay to do the payments in all the counters. You don't have to carry anything extra, right? And can you guess what is this? Yeah. Any other guess? That's a weighing machine kind of a thing. You stand on that and it will do a complete body analysis. It can do your body mass index. It can do a bone density analysis. It can do complete annual kind of a thing. It's a healthcare device. Okay. Right. So the thing around us, everything you talk about, we are seeing it very smart. And let's see what is electronics part of it. But before that, let's see the news around us. What can you imagine? What is this? I'm sure all of you would have. Okay, what is this? ChatGPT. How many of you have used it? All of you are using it regularly?
After screen visiting.
Why? Huh?
It makes us dependent.
But still, you should find. I mean, to upgrade it, you should know what it has, right? What are the features and how you can use it also, right? Anyway, that's the chat GPT. We are, I mean, these are the various newses which we see around us. Let's see what are the takeaways from this. What's happening to Apple? Apple is continue to replace the suppliers' technologies with their own. So that is a trend we are seeing, right? Apple was just a mobile device supplier, but today they're making chips, right? The traditional chip makers are Intel, Qualcomm, and all. But today the kind of companies which are getting into chip design are Apple, Google, and all. You can see here Google is building its own chipsets for Pixel 6. And we have companies such as Meta, Amazon, Microsoft, among many others who are getting into semiconductor designs, right? What does it indicate to us? Let's see. And you can also see here, see, it is not that it's overnight it has happened. It had a complete 15-year partnership with the chip vendors. Right? And we believe that Intel is the market leader, or nobody can beat Intel. That's the perception we carry, right? So today, Apple as a new entrant, so we struggled for years to saying that it is a barrier for us to getting into semiconductors or any new domain for that matter, right? But today that is no longer true. Anybody can do the chip design today, right? Why are we going into that situation? Let's see in a while. And smart everything. We just saw a couple of examples how we are seeing everything around us becoming smarter and smarter day by day. And and what are other news we are hearing now? We are seeing that to build a vibrant semiconductor and display design and innovation ecosystem, India has come out with the electronic mission, right? Semiconductor mission. That is a thing which we are really, the government, from government angle also, it is pushing in a great way. And Chips and Science Act in US, which was signed. So that also is really a game changer. That's what we believe in, right? And this is what we hear around us, what is happening. And India, US just signed a MOU yesterday, right, for our semiconductor solutions. Now, some more news. Again, even in Karnataka, we are getting analog design, the fab house in Mysore. That's a news. And then we have and then there are 2,000 chips being designed every year from various design houses in India. Right? Can you believe that? 2,000 designs. You can see each design takes so much of effort, right? And these are all complex designs. So that is what we hear, and we see 20,000 engineers are working on various aspects of design. Okay, so that's a kind of a, if you see the cumulative requirement of over the years, and if you want these 2 or 3 fabs getting running full capacity, you can imagine the kind of designs which will come out of India, right, in near future. So what does it all these indicate? Again, there are talks that Reliance and HCL are also considering getting into semiconductors. We are also seeing that Vedanta is already, Foxconn has already signed a deal, right? And they have also already started working in a place to set up a fab. So all these, what does it indicate? What does it indicate to us? Let's see what are the takeaways from this. What do you feel? What is happening around us with all this? What are your takeaways? Can you all guess? Now I showed you so many breaking news which is happening over the currently around us. What do you get out of this?
I think entry barrier is getting reduced.
The boost to semiconductor, and then what else? Yes, then that is anyway, we have been seeing it. Technology is everywhere. We carry with us, right? When you can't really come out of the house by forgetting a phone at home. We feel that we have left our breathe, we stop breathing there, right? So we just go back.
Opportunities are there to work in this area.
Yes, opportunities, and then what are the
Independence.
Madam,
Yeah.
we are actually progressing
Yes.
towards Atmanirbhar
then?
Bharat.
For opportunities for startups.
Yes. Okay. So of course, all those are opportunities is one part, but what is happening technologically? Technologically, what is happening?
They are becoming self-reliant.
Yeah, every company, every product house is becoming self-reliant on their chip designs in VLSI as well, which we thought. And what is, how does it translate to the architectures, right? System architectures. So can you guess this architecture where it can go? I'm stating here that all these designs are, I've picked it up from the online sites. Okay, all these designs are not, they are available online. Not mine. So this interconnect based architectures, where do you find them useful? Yes, then large computing. Where are the large computing?
Super.
Servers, cloud servers, right? So yeah, and where do you find this? That's okay. You can see this is the sensors all around. You can go into this IoTs, right? IoT.
Ma'am, IoT in medical healthcare.
So you can see the various IoT flavors here. IoT Edge has a different architecture, IoT Consumer has a different architecture here, and then at the cloud interface, you have a different architecture. Even in IoT, you need a specific requirement for a specific use cases or applications. Application specific system on chip is what is required today. And again, ring interconnect, all these interconnect based systems are cloud servers where you need a huge unlimited computing power. So we saw the various spectrum of architectures which are required, which are really fine tuned, or the performance is tuned to a particular application, right? And what are the key takeaways from whatever is happening around us? Everything is becoming smart. I'm sure all of you agree to be on this. And systems can be small to large in terms of size, but complexity wise, even the smallest system is equally complex. A smallest system which we do it on the chip is equally complex. Okay, the systems are becoming smaller and smaller in terms of size. The complexity is increasing, and system requirements are application specific. So requirements are driven by the applications. It is not just the system requirements. We used to have a system requirement and then we used to have a hardware specific requirements. We used to take that forward, forgetting what software does, right? Eventually at midway of the development process, we used to really understand what software requirement is just to the extent of interface design. That's it. Beyond that, it was left to the software architects and software teams to develop the system. But today what's happening, we need to cater to the complete application as a system, right? We have to tackle it as a complete application as a system. So the system requirements, the scope of system requirements has widened. And then of course, complexity has increased manifold. Reusable ratio is phenomenally increasing. What are we saying that? Why are we saying that? Any guesses? Shorter time to market. So we need to just buy out of the shelf IPs and then want to integrate, make it rich, because we can't start everything by scratch and still meet the time to market pressures, right? So the ratio of reusable subsystems, that reusable cores, which is really phenomenally increasing in the system. That's how we build systems today. Unlike earlier days, it has to be very hardware specific. Okay, make and buy decisions used to be very simple. Okay, processors and non-critical IP cores we used to buy. It was that simple. Today we plan to buy everything around us, whatever is readily available. We want to pick and integrate it, and then add, because our target is the application. Our end goal is the application today. And then change in design. This, of course, requires altogether different way of design methodology or the development methodology, where we can't rely on just system on chip architectures, but it has to be a solution architecture. Solution architectures gives us advantage in a sense that we can optimize it to suit the particular application or the use case, right? Which we never thought in earlier days. We used to design chip and then we used to make software do their part of it. And then finally, we used to cater to the solution. But today it's not the case, because the optimization requirement and the design application specific requirements are huge. And then the system designers have to really fine tune the solution to suit the sophistications required by the application itself or the solution. So it requires a solution architecture. So do you all agree that there is a shift happening from the design angle or the development angle from the systems on chip design to the solution on chip or solution approach of design? Yes, right? Are any contradiction here? No, right? We need to really understand, look at it as an integrated problem or a global problem. So let's see how we have progressed. We have hit this condition or in this scenario today. So no talk ends without quoting Dr. Moore's law, right? So yeah, so we have been for decades in the past, we have been working on scaling as a problem. And today also scaling has really led us to a lot of trends, which we are really addressed it phenomenally well so far. And we have even beyond CMOS, we are addressing with device structures. Right, new device structures are many. There are many new device structures which are coming here. Tunnel FPDs, carbon nanotubes, and there are gate-all-around structures. We have many device structures which are getting innovated, and then we have invented, and then we are adopting them. Okay, still the scaling is continuing. What this is? Scaling is still continuing. We are still hopeful of continuing the scaling down. Even last week, Intel proved that 1.8 nanometer technology is they have demonstrated that, right? So even the ITRS talked about this. I'm sure that all of you are familiar with this graph. And we had this more than more, which is basically diversification, where we have a collection of different technologies, CMOS compatible technologies we call integrated, like sensors, MEMS, and all we integrate. And then we have more, which is basically the miniaturization, which is scaling driven trend. And then we also talk about the beyond CMOS, which is altogether a new device structures, altogether a new device, which are equivalent to the CMOS like transistors, which can behave and continue to help us in developing newer systems or solutions. So this is the trend. We've been predominantly driven by the scaling, right? So far. And now we are almost thinking that we have hit a roadblock. So we have to find new ways of doing, but still we continue to address the complexities of the solution we want. Okay, so we still want to develop the solutions which are tailor-made for the particular application. So we figured out two things now. One is the paradigm shift from systems to solutions. Secondly, we are hitting almost close to the scaling deadlines. Though we are still continuing, we are hopeful of creating new structures, but still we want to really make sure that our system addresses the solution aspect of it. And yeah, beyond CMOS, of course, in the scaling trend, we have newer devices. We could talk about the spin wave device and spin torque device. There are a variety of flavors in various devices. Spin FETs and tunnel devices. There are many kind of new device structures which we are considering beyond CMOS aspects. Okay? And magnetic logic. We have various varieties of new inventions which is happening in the device structures. That is beyond CMOS trend. Now, yeah, but even on the technologies, the scaling complexity is also increasing. Still, we are trying to scale it down and making the scale down technologies useful for the solutions, right? Today, even if you see Intel, Samsung, and Qualcomm kind of companies are still driving the scaling and trying to work towards making the deep submicron technologies available commercially. So we are still chasing scaling. That's what it means here. Yeah, again, yeah, various device structures. I'm sure all of you are aware of these device structures, gate all around, and there are various varieties of FinFETs, and again, 3D structures are all available today for the system integration. And one point to note here is we traverse from planar to your lateral devices to now vertical stack structures. That's the trend we are seeing even in the device structures, right? We are stacking even at the device layers, right? To address, to still continue to take advantage of scaling. Okay, technology. And even if you see, for us to go to place to see about the roadmap in semiconductors has been always ITRS, which got renamed to IRDS now because looking at the trend, it is solution oriented. So it's no longer semiconductor oriented, right? So they are publishing the roadmaps, including for devices and systems now. And let us see how that trend is going forward. Okay, if you see here, the initial 2012 roadmap of IRDS had this many subgroups, I would say, are the focus groups, they call it. Okay, focus teams, they call it. So they have process integration, which we call that lot of inventions or innovations to happen by integrating the process related stuff to the design aspect of it. We call it as left shift way of addressing the challenges, design challenges. That used to be the focus in defining these focus teams. Okay, where we brought in a lot of process related fine tuning stuff as a design rule to the design methodologies. That was what was happening to cater to the advanced technologies of deep submicron. Then we have system drivers and design. Again, we started addressing the system level challenges, and hence we talked about more than more and then beyond CMOS structures, right? That's how the trend got pushed further. Then factory integration, we studied a lot of factory related stuff. We tried to bring in even the packaging problems we tried to solve in the design methodology, Then, yeah, more than more also involves MEMS device to be integrated into the systems of the solutions. Then emerging research devices, I talked about a lot of new device structures, which are also, again, as an extension to the scaling complexities. Yeah, new emerging materials. There are many new materials being tried out as a. So if you see the trend which has happened over the years, we cater to the addressing the problems of the scaling all along. Okay, and still we are pushing to really achieve our dreams with scaling as a prime objective. And we saw a lot of problems on IC interconnects. All right. So again, some more angle to 2012 roadmap, which was declared by IRDS. So here also, they started looking slowly towards the system. So we addressed the device areas, the device structure related stuff, and then interconnect related stuff, tried stacking transistors, and then tried to work on the interconnect challenges, right? So all those were the focus points in a previous roadmap. Okay, just one previous roadmap. So just to classify, give you a bigger perspective of scaling, what we addressed. So we had three types of scaling. The first type of scaling was geometrical scaling. Geometrical scaling is basically just look at the device as a structure and try to scale it down with an equal proportion. All the parameters in equal proportion. That was the first, that's how we addressed the first challenge. Then we said that it's not required to scale down every parameter of the device, but certain parameters can be left out in terms of scaling, but just consider the horizontal parameters which can be scaled down. So that was a new thinking which happened from 2003 to 2024, which we still are working on. Okay, and then now we are talking about 3D power scaling. This comes from the fact that we need now the heterogeneous integration. We can no longer do it with a monolithic or a single type of structures. Scaling the kind of problems which is really we are getting, the systemic problems as we call them, right, cannot be addressed by just the scaling trends, right? That's why we are talking about 3D integration. So if you see the trend which is happening in 3D integration, all of you are familiar with interlevers and those kind of 3D structures. 3D stacks, where we want to integrate the conventional devices, and above that we have an interlevel layer, and then we have interlaser a layer, and then we want to put again a memories, a flash, and different. It's a heterogeneous integration, we call it. Stack them together in a package. So that is a new trend which is happening. Okay, so scaling can be divided into these three classifications. Now, beyond 2020, again, 2015 IRDS roadmap, what it has added is one extra thing is the outside system connectivity. So that helps us to define, that's another focus team which is working on connecting the heterogeneous systems, subsystems, I would call it. Again, each subsystem has become a system itself when you compare it with the previous roadmap structures, discussions. So outside system connectivity, again, there are a lot of options. How do you connect chip to chip now? How do you connect die to die? Right? There are many ways being thought of: optical connectivity, wireless connectivity. There are a lot of options are being tried out to really realize the heterogeneous systems. And then customized functionality. This is where the trend is going towards the solution, right? You want a customized, see, the requirement of an automotive SOC is different from the requirement of a server SOC. A requirement of a mission critical SOC is different from the requirement of a simple home control IoT. The complexity wise, yes, all have to have its own challenges to realize it. But the requirement when you are talking about the control or the freedom, the figure of merit, or the freedom which which any designer or developer need to optimize a solution for a particular use case is the demand for such freedom is too much. We need that kind of freedom. So there are focus teams getting defined in IRDS, which is working on outside system connectivity for heterogeneous connection, and then customized functionality. And again, the heterogeneous integration, which talks about CMOS compatible technologies, and then various other technologies which can go into the system as a solution. And of course, it also needs to consider the outside stack of the operating system, the softwares, and the kind of requirement in the full stack level of software as well. Okay, up to the level of actually applications. So these are the two extra focus teams which got added in the roadmap in the current roadmap defined by the IRDS. It got defined in 2015. Okay, that's here. Alright, you see that's all are similar we have seen in 2012 roadmap. Okay, so device trends again, to realize the device beyond CMOS, we have the material considerations as well, the alternate material considerations to silicon and whatever high K materials which we used to use earlier. We are trying out on the tin oxide, high power gallium nitride, and there are various material wise also people are considering various alternatives. Okay, these are the various process nodes which are available for the future solutions, I would say, because all these are getting commercially viable today, which we never thought that these are realizable. Because if you see the second law of Moore's law, what did it state? Stated that the manufacturing cost will be so phenomenally, it's exorbitant, such that even it will not be commercially viable to realize such devices. What was the second law of Moore's stated then? But today we have gone beyond that, where we are saying even 1.8 nanometer design can be realized commercially. Commercially, we can, the Intel is setting up a plant for the 1.8 nanometer, right? So yeah. So we are already talking, at least in talking terms, on the angstrom scale devices, right? That's what is the trend we are seeing as of now. We are still not accepted that we have hit the end of scaling. Yeah, again, what we are seeing in the device structures, there are various device structures, alternatives we are seeing. Okay, and we talked about the paradigm shift from systems to solutions. So how much of that is semiconductors, right? We are talking, our relevance is semiconductors now. Is that all the solutions require semiconductors? The answer is yes. The answer is 33% of the solutions require semiconductors. So it's electronic systems, again, electronic and even the mechanical. If you see, the cars are more electronic today than the. So if you, the 33%, it's a 2021 statistics, 33% the solutions, most of the solutions. So that means that it has become we need semiconductors there in every solution. Okay. Okay, so the scope of IRDS, how it has increased, the trend shows us that it is a clear paradigm shift which is happening from the chip to the solutions, which states that you can see here, this is giving us with 6G and all, it is giving us unlimited computing with cloud servers, right? The entire cloud servers is at your disposal as a developer if you are a solution architect or solution designer, right? The entire cloud, you don't have to worry about your laptop, your system power, your system capacity or the performance of the system, etc., etc. You have the entire cloud accessible to you. So the computing power is unlimited, right? That is a design environment which we are working on. And we also have faster interconnection, faster communication channels to reach out to the cloud, right? That is also, we are seeing that trend. Then you have deep learning. I'm sure that with the kind of a scaling complexity, we have moved beyond scaling and the systemic complexities, where we needed an integrated platform for design, which is undoubtedly true, right? We all need that kind of an environment, and we cannot claim that, okay, I'm a VLSI designer, I'm a semiconductor professional. No longer you are a semiconductor professional. You need to understand cloud, you need to understand intelligent systems, you need to understand software, you need to understand application layer as well, right? You can't just say, you need not be specialist, but at the same time, you can't just say that, okay, I am a hardware, I am software. Gone are those days where you can just have yourself in a box. Yeah, if you see here, the IoT computing, it also comes with a lot of other challenges like the security, the encryption, a lot of other things which we talk about generally, right, as a separate specialization are required even when you talk about solution. Okay? You need to look at privacy, you need to look at security, you need to look at the design process, you need to understand the other person's issues, bring in everything and make sure that the design process, the current design process should consider what has happened to the design in the previous phases and what is going to happen to in the next phases of the design development cycle. That is all every phase of the design has to do that, has to know what are the various processes which is going to happen in future. So we have to have a unified or the integrated approach to the development. Yeah, the high-speed networks are required because we are talking about heterogeneous integration and data centers. We are talking about cloud computing environments, and we also have to develop SOCs for such systems further. So if you see the entire IRDS scope has enhanced from simple VLSI solution to the entire application-oriented solution. You talk about more than more, which can cater to all medical, healthcare, smart city, smart home, everything, all such applications. You talk about high-speed networks. It talks about all sorts of communication related technologies you need to know. So, yeah, if you see here, a solution architect should know the entire section of the entire specializations. He may not be specialist in each of them, but he should at least be aware of what goes where when you are providing a solution. Okay. So yeah, so what does it mean to us? So there are various solution approaches. Right? There are different solution approaches which are possible, and there are again, you have to consider every possible way to provide the solution. You can get the solution, you can get the answer in any of the related related systems. So that's what this talks about, multiple specialized architectures. So what you need for doing this, you need an exploratory framework, right? You need to do space exploration, you need to do timing exploration to arrive at what is the best solution possible from various alternatives I have around me, right? How do you do that? You need to model the solution. How do you model the solution? You need to do a lot of computational analysis, analytical, and you need to have a lot of data in the past data and the current data. You need to collect, feed it, model it, and then analyze it, and then use it for development. So these are various trends you need to look at. The options are huge. That's what I want to tell here. The future systems, how would our future systems look like? Is that really it is important to, these are the inferences from whatever talk we have done so far. No single component providing all functions, which is very true. We need to look at various alternatives and integrate them, and increase system complexity as number of subsystems increase, right? I mean, the only way to do the solution approach is add more and more subsystems. Each one can be it need not be in the same homogeneous technology, but it can be from the multiple technologies. And system integration, of course, is a dynamic process, continuously evolving. So, but our approach has to be from solution orientation. Okay. And yes, it is economical to build large systems out of smaller functions, separately packaged and interconnected. That is one approach. Other approach is optimizing it by interconnecting them, stacking them, and then making a heterogeneous. We cannot talk about the second option now only because we are just entering into that space of solution offering. So monolithic, homogeneous, and heterogeneous integration at the die level or heterogeneous integration at the package level. Both are being tried out. Both are the option for us. Okay, do we do it at application stack? Okay, entire stack. And it has to be addressed case by case to optimize the entire solution. System performance is, of course, determined by the harmonious confluence of the hardware, architecture, and software. So our architecture should be perfect. So where you do the modeling of the entire solution, then decide. So it was simple as a hardware software party for us earlier. But today we are talking about the solution. So this complete solution architecture, when you're modeling, you have so many components here, subsystems components, which you need to individually and equal amount of design decisions you will be taking, right? And you need to ensure, and the entire performance of the solution now depends on so many subsystems, okay, in totality. So that is what it takes, and the complexity to that extent has increased. Then, yeah, application-specific solutions are way forward. You can see that in various classification of the solutions we offer. IoT edge devices has importance of security and a lot of other things, small amount of energy it should consume, okay, and interface to CMOS compatible technologies like sensors and actuators, etc. And AI capability is a must in all IoT systems because that is
We are not hearing.
we use for financial transactions. We
Could
use
you pause for? Actually, through the last 10 or 20 seconds, the audio was gone. So please.
I don't know where I have to start, restart.
That's it.
All right, I can start from this slide. Am I audible now?
Yeah.
So what I was talking about is the heterogeneous integration is the way forward, and the solution approach is the way forward. And to do that, to ensure that the entire solution is optimal, energy efficient, and optimally performance driven. So it is required to ensure that each of these subsystems are equally efficient. And
Again, we are not hearing.
so it will not be just a system on chip, but it will be a solution driven. Okay. So that I was giving explanation of the classification of various solutions. We can easily classify them to be IoT devices, wherein the requirement wise, if you see the security and privacy are important, and the interface to heterogeneous CMOS compatible devices, which is also important. Okay, like sensors and actuators. That's where I was talking about. And of course, it has to be energy efficient because there are small IoT systems. And then it has to be AI capable because all things around the user has to be intelligent, equally intelligent as the user itself is. And personal augmentation system, if you see the present challenges which it poses to the designers are basically the faster turnout time. That means the development time. So a user keeps wanting to change the devices faster, right? So you need to really keep updating the designs faster. So your development cycle has shrunk. So how do you make sure that newer and newer devices come out so fast, right? Development cycle shrinks. And of course, you need to really give more and more functionality or the sophisticated applications running on the solutions faster, and so time to market be slower, faster. Yeah. So frequent releases, and here, mind you, I'm talking about the solution in total. Okay, you cannot say that the chip has a problem, I need to get the chip taped out and then software. No, you have to have the next releases as a solution as early as possible. So the time to market is for the solution, no longer for the chip. And financial transactions, telemedicines are all demand high security and privacy, which is very important. Or otherwise, all your personal data will be really misused. So then the cloud application, the challenges are different. They take heterogeneous integration issues. Right? There are a lot of heterogeneous systems. There are hundreds of processors, hundreds of computing resources which are there. So, and you need to have, and the huge amount of data it stores, right? Huge amount of data it stores. What happens if it stops for a while? Not possible. So we can't afford to do that. So you need to have that kind of a secure system, backup plan, backup solutions and all. They have to balance the performance improvements of chosen applications provided by specialized accelerators. So you need to, each of this what I talked about itself is a problem on its own. Okay, itself will be a huge challenge for the system developers. And the problems, especially of heterogeneous architectures, it can provide a most efficient solution, but that is true. But of course, it poses equally challenging challenges to the designers. Yeah, outside system connectivity, again, newer technologies, newer integration techniques. Okay, how do you really stack them, interconnect them? There can be many stacks, many layers you can go on stacking to make a solution possible. Again, each of these, as I said, each of this can be a challenge in its own. Like when you are talking about RF, the challenges are different. So when you're talking about high-speed digital, the challenges are different. When you're talking about analog, challenges are different. So one needs to address all of them when you're talking about the solution. Okay, so what is the kind of a support we are getting as a designer from the EDA platform? So all these decades, we were talking about scaling complexity, right? We catered all our design tools really bothered about how efficiently they address the scaling complexity. When I say scaling complexity, making the devices denser, right? Packing more and more transistors in a unit area. So that was the focus on all the design tools. But today you need a complete framework as a solution framework for us to design. As I said, if you're talking about synthesis, it should look at all the RTL related issues to synthesis, give you the better netlist. And it also has to consider the physical design issues or challenges. Like, will it cause the congestion? Will it really help me to do the clock-free synthesis? Will it really solve my timing problems and all? To completely run the flow virtually, at least to gather that information, feed it back to the current process, and then make the best decision out of it in picking up the cell library cells or whatever you want at that point. So every process step has to really evaluate the past processes and also subsequent processes virtually, and then take those problems or the challenges, feedback, and then do a best job. So it is an iterative process, and it is a really complex, and only intelligent designers or developers can do it. Okay, so yeah, and smarter EDA, of course, these designs solutions. When we are talking about solution level approach of the designs, it cannot happen with a single database system, which we always used till now, right? When you are addressing the scaling challenges, we used to do repeated runs, and these tools will throw gigabytes of data logs, okay, which we used to solve, and then move forward to the next step, right? That cannot happen, because when you're talking about the solution, you need to look at alternative solutions, because the modeling, when you have done, you have tried so many alternatives to arrive at a particular, you have taken a couple of assumptions and then arrive at a particular solution architecture, right? So you need to ensure that at least the current solution architecture is much better than the previous solution which existed, right? So it cannot happen with a single database structure. Are you getting my point, what I'm trying to say? So initially, when we had a soft design flow, we just concentrated on that design. We never bothered about what happened to the previous designs which we had done, right? We just went through the database which was relevant for the current design. Here, what I'm saying, when you're talking about the solution level, right, you need to look at the various. For example, you are talking about the placement. Placement is okay. You figure out by doing trial and error and do the placement. But that is not enough, is what I'm saying. For a previous AI chip, probably you would have used 100 iterations and you figured out the best optimal placement. So you can take that knowledge here and adopt it. So it requires a multiple set of intelligence learned from the data set of the past, right? So those the tools have to be so intelligent. The tools have to consider multiple runs information or the learning from multiple runs of the designs. Okay, multiple runs of not the same design, but multiple runs of different design, and then adopt to optimize the current solution. So that is what I'm saying. It's smarter EDA when I talk. Okay, system level modeling tools. It was easy for me to say that, okay, you model alternative solutions and then pick suggest the right solution. How do you do that? Such a complex thing, right? So that is what you should have, a modeling framework where you consider all software architecture related issues, design related issues, hardware related issues, and then you adopt the modeling structure. So you incorporate all of them and then try to help you to make the right assumptions and then take it. So that and design for context. This is a design for context, which talks about you are making the solution optimal for a particular application, right? That requires EDA tools with greater interoperability. I may use modeling tools from some vendor, design tool from some vendor, and verification tool from some vendor, and the validation tool from some vendor, and the factory interface sign-off tools from some other vendor. So all these should understand the databases, each of these tools throughout, right? To give you the correct flow. So that is what I have been referring here as interoperability. And also to the manufacturing. We are also concerned about this solution being manufactured, fabricated. So even the CAE also, the engineering also comes into picture. And then, of course, the entire set, the validation counterparts. Yeah, the verification. Design and development framework require a better integration of tools. Right? You need a complete perspective. You need a framework now. It is not one synthesis tool. It is not one timing verification tool and all. Each of this should consider what happens if I change the thing and then suggest you. Okay, give you options. Yeah. So these are the trends we see in the EDA design. So if you see the entire solution architecture flow, so how does it look like? Okay, suppose I decide to provide a solution architecture for one particular problem. How does it look like? You do a requirement and initial sizing and complete architectural exploration you do by modeling the entire solution. Okay, and then decide on the specification, architectural decisions to take, and then you will just arrive at the thing. And then finally consider the complete software related architectural issues, address hardware related architectural issues together, and each one knowing the other counterparts challenges, and then give you a direction. And then finally, you have the complete simulation and optimization framework where you can really get into the action oriented design. I don't know whether you got my point, but this is the in brief at a 50,000 feet above way of design methodology for the solution architecture. I mean, again, this is from the Siemens blog. You can see the kind of, and of course, just the, I'm sure all of you know the scaling, what we are talking about. Almost we are talking about angstrom nanometer technologies now. Going beyond, I'm sure in your career, when you are 30 years down the line, after working, I don't know where we will be going, what kind of systems we have, right? What kind of solution you will be designing. That's the that's what this scaling, what has happened so far. Okay, solution approach, identify the problem. So so just a practical tip, I would say there's no point if I just talk about fancy things and then go away. So what I would want to really get to the point is that identify a problem of your interest, just to have a hands-on flow of this. So identify any problem of your interest which you would like to solve. Come explore the probable solutions. I mean, I'm referring to all electronic solutions here. Okay? So, and analyze the existing solutions. What kind of a unique solution you can come up with? Okay, you don't have to design it from the scratch. See the available options, like improvisation. If there is a solution available, see if you can. Or do you really need a radically different solution for it? So that you explore, and then that's the exploration part. Then comes the model solution, where identify a modeling framework. So how do you exactly work out? So if this is a problem, what kind of solution you would really dream of? So that is another thing. And then the tool platform, identify various tools which you can make use of. There are a lot of open source tools which are available to try out a lot of these things. Okay, you can pick and use them. Find out a framework, what all the various set of tools which will be useful for this. Right, that you can list them and see if you can really try out with them. Then available subsystem models. Find out what are the available subsystems you can pick. Again, I'm not telling you don't start from scratch, but you can always pick the various interface scopes and then try to bundle them together or integrate them together. Then I similarly identify hardware subsystems. Okay, find out the IP cores which are available. A lot of open cores are available, which you can just pick, integrate, and see what what kind of a system you can create, okay? Which everyone can do it, which we never thought of. 30 years back, we never imagined that a VLSI design can be done at home. Today you can do that, okay? With a lot of options available. And then identify the subsystems, type of subsystem, find out in what format they're available, whether they're hard IP cores or soft IP cores, what kind of cores they're available. Try to integrate them together. See what solution system you can bring. Even if you bring out an existing system integrated, one processor, memory, some cache memories, and some kind of a interconnect, and then simple interface cores, if you connect together, forms a system. Okay, it forms a useful IoT system. Okay, you can really demonstrate. You can create a system. Then find an integration plan, and then integration development. You can integrate and check it, and then finally verify it at the subsystem and system level. You can try it out, and then design and development plan, work towards hardware development. Make sure that it is you can really use a kind of a what do you say? If you make it compatible with the existing systems, you can reuse the entire software development environment. I'm giving you tips, okay? You can try this out. If you can make a system, IoT system, which is pin compatible with Arduino existing thing, you can really use the complete Arduino software development environment. The tips, okay? You can try it out. So software development, plan that out, and then you have the simple system in hand. You can get to fabricate. So yeah, then go for prototyping. Find out there are a lot of options for VLSI today. eFabless thing is available as a pre-source, and then today they have announced. I think last week they have announced Chip Ignite program, which is again 10 millimeter square kind of a free space on silicon, which is available to you. Just see, you can mix and match this course and then submit one, and then yeah, get the feedback on changes required. Then it is an iterative process. Nothing works in one go. Okay, you have to have a lot of patience to do. And yeah, find the development plan and explore open course at every level. Don't start from scratch. See available things, mix and match, and then you can make a system. So verification platforms also, and you can find a system. Okay, finally, it's my favorite. These are my books. If you feel whenever you have time and more energy, you can just refer them. And then, yeah, I think this is the last. There are links. I've shared the PPT, the team here. Thanks for patient listening.
Welcome back, everyone. So we will be taking the questions both online and offline. So if you have any questions in the online mode, please raise your hands and we'll turn on your mic. And otherwise, if in offline mode, if you have any questions, please feel free to ask. I actually had one question. So yeah, you talked about how the SOC in SOC to solution, both hardware and software is required to understand. So, but the problem comes for a system of this complexity. How do you prepare the models for it? Like where to start? Like which type of model do you use for understanding the end to end from software to hardware? So, are there any challenges there?
Of course, part of the solution development is non-challenging. Everything is challenging. So modeling, there are a lot of modeling, system level modeling frameworks available, which has various tools. So you can use them individually model. Suppose, for example, you want a processor subsystem, want to model. Then a lot of MATLAB can be used. So a lot of modeling tool frameworks are available, which you can use them, and then especially we use that in analog designs a lot. Okay, to design on configuration, design to take decisions on the bus weight, all the things, right? ADC and all, if you are talking about the big size and bus weight and all. So we use these kind of modeling techniques and then use it as a configuration spec for the design. So we derive the configurations by modeling. So you find out the spec by modeling them using this system level modeling. Like if you are good at System C, you can even develop your own models. There are a lot of models which are readily available. You can pick and place them, and then you can use them. The best part for modeling is that there is no constraint that it has to be synthesizable, right? You can integrate any kind of the models of any high programming language. Can System C, it can be even Python or any model, any form models can be integrated. I can use them.
Any questions?
Yeah,
Yeah.
yeah, please, take
Sir.
question.
Ma'am. Ma'am, I have one question related to, ma'am, you are talking about the high-speed networks this system will require. So, what kind of high-speed the optical, the free space optical networks we can use for this type of devices?
Can you repeat the question, sir? I didn't get your question at all.
Ma'am, I have one question related to you are telling in one slide that the high speed networks, that is the fiber optics networks, the photonics network. So you are basically telling that the communication, for the communication purpose, we are using here the fiber optics network, that is basically the free space optical networks we are using.
No, I'm not saying we are using. That is one of the options which is being explored, what I said. But having worked in EPON technology, I have worked on passive optical network technologies earlier. So that is the PON network which is being used for the switching systems, for switch level network, right? There are optical transceivers which are available, which can be integrated, and it has its own specifications, like standard specifications which you have to comply with.
Okay, ma'am.
Am I audible now?
Yes, ma'am. You are.
Yeah. So there was a question, if I have to start some design now, how do I go about? Because I don't have access to tools, I don't have access to codes and all, do I have to start from the scratch? So my answer, I was trying to answer that question. So the question, the answer for that is you go to open course. There are a lot of open course available. Even on the EDA playground, there are a lot of projects available to start with. Okay, definitely you can use them. You can download them, simulate them. There are free simulators available. You can simulate them, see, make it work. That's the first step. And take it out from your mind that you need a lot of support from SAFL or government or somebody else to do your work. No, that's not required today. To prove that you are a good VLSI designer, you don't have to go out. So you can do your own SOC design and make it work. There are a lot of options from sponsored programs where you get a free space on silicon. Multi-wafer programs are there. Multi-chip programs are there. Okay, MPWs we call them. So where multiple projects can submit multiple projects to fabrication. And then you get it, they fabricate it for you. Okay, they allocate a certain space. You have to use their course, okay, to make your system. So you can do all that and then submit it, try, you can sit at home and design a system. Then you go to SAFL, and the minute you prove that you are a good VLSI designer, everybody will come forward to grab you. Either they grab you or they support you. That is for sure. Because there are a lot of requirement in VLSI design itself. Design. Did I answer the question? So yes, online, anyone?
Yeah.
Ma'am, I have one basic question. Ma'am, can you please explain once the concept of reusability? Here you told that the reusability is done in this case. So can you please explain?
Yeah, I meant because of demand for shrinking timelines, time to market, we don't start any design from the scratch. Okay, so we try to use, for example, USB cores. So there are a lot of USB cores available, either open source or off the shelf. You can go to these vendors who have already developed targeting to particular technology and they have proven these cores. Okay, making that course work.
Okay.
So you can
Okay.
just buy it if you are, if it is affordable to you, or you can download it from the open course, make it work,
Okay.
and then you can use them. So
Okay.
initially, if you see VLSI development, right? The technology was far
Okay.
ahead. The technology was shrinking. The device size was shrinking. There were a lot of transistors per unit area. So the transistors were available in abundance, but there were no designers to make use of them. So that was a design product, call them. So to bridge that gap, what we did, we started reusing it. Even if we need one USB core, we bundled many USB cores because we had so many transistors available in the wafer. That is a reuse. Whether we want it or not,
Okay.
we used to bundle interface cores. Like if you see all your laptops and all, it has multiple USB cores, multiple UART cores, multiple COM ports and all, right? We used it. Nobody had asked that I need 2 ports or 3 ports. We have bundled it because to make sure we use the transistors available from the technology. Technology was granting us a lot of transistors and logic cells, so which there were no designers to use them functionally. So that was the reason behind the reuse concept, and reuse also helped us to reduce the time to market.
Okay.
Yeah, that's the
Okay.
approach. We want a lot of these reuse cores to be maximized. The number of reuse cores we want to do is maximum. Have a proprietary, because even we can create uniqueness even in the application stack, even in the software stack, right? So that's the approach we put in the solution.
Okay. Thank you, ma'am.
Okay.
Any other questions? Yes.
One that I have. Yeah, so we see that with the advent of ChatGPT, a lot of industry and job prospects are getting disrupted. So keeping in mind the fact that much of the design automation of design and development is already automated, and we mostly just give in some of the cues. So if we have such an intelligent program which can actually automate much more of that, then do you see that ultimately the job of humans will just to be given that we need this input and that output, and everything will be done by the system itself?
What do you feel? What is your personal opinion?
Uh,
Can any system take away human intelligence?
uh,
Yes, artificial intelligence can do a lot of repetitive jobs. It has a lot of patience. It doesn't have a kind of a lethargy we get, the kind of monotony we get, right? That is agreed. That is taken for granted. Yes, Chat GPT can be used in every possible way, even for our design. But still, do you feel that it can overtake you? What is your personal? I mean, do you have fear that okay, I don't
in terms of being creative, I can understand that humans cannot be surpassed, like to come up with new solutions and different approaches to problems.
You tell ChatGPT to do one of the products which I showed you. Can it do? I mean, it is that okay. It requires a human intervention because it is a human who wants to use those devices. It's not ChatGPT which is going to use, right? So at that point of time, yes, make use of ChatGPT also. Today, I just wanting to try what will I talk here because SOC to solution. I just asked ChatGPT. It gave me a beautiful tech summary. Gave me a summary. That's good enough. That's all it can do. It cannot give 1 hour of lecture. Even if it can write repeatedly 1 hour, it will not be effective. It cannot take away my experience or my hands-on things.
Yeah.
My challenge solving capability, issue solving capability, what I have over the years, which I have gained over the years, ChatGPT cannot solve. It can just say that, okay, Veena had solved it this way. So can I try that? It can do that. No doubt about it. It doesn't have that intelligence that this is the solution which is going to work. There you need an interruption. So, and especially this is high tech, right? And ChatGPT when you are using it at the surface level now. Yeah, it can gather all the open source information and it can package it well. It can packaging it to the way the humans can read and appreciate. To that level, it can make it sound good or look good. You can't replace a human. My belief, I'm sure many of you have that belief, and this is a generation who is going to define how do you want to use it. Do you want to get scared and go back, sit back, or do you want to really make use of it and then go forward? Right? Hope I answered you.
Yeah, yes.
In all this will make and help designing their end-to-end systems. Right? How do you
Very good, right? And you can also, suppose you have a requirement, you can do your own chip, which is very optimal to your requirement. Tomorrow you want an agree device. You know your requirement better, right? From that angle, your requirement, you don't have to go to a vendor, tell him that this is the agree requirement I want. You don't have to go to a Intel or a Qualcomm or a Samsung to do that. You know your requirement, you can design sitting at home, right? I mean, sitting wherever the risk goes. I mean, the whole point is, as a solution, the solution will be optimized from the entire solution perspective, right? So you will have energy efficient, high performance, very relevant for the application. Because what is Google's interest? Google's interest is not general purpose computing. Google's interest is his search engine should be good. His information processing should be good. That is its requirement, right? What else it can do? Right? I mean, it really caters to his requirement. The same is the case Apple. What Apple wants to do? It wants to make its mobiles so smart. That's it. It wants to make it health conscious, health monitoring device. It has its own plans, right? Roadmap. So they want to optimize the solution to suit their thing. That's why they cannot use general purpose processors which Qualcomm or anybody else design. So they want to really have their own thing. So optimized solution. That's the approach. That's why that also gives you a lot of opportunities. Right? Yesterday years we had only Intel, Qualcomm, and a couple of fabulous design houses for us to try out as a VLSI designer. You people have any company, you walk into any software company and say, okay, I will design a chip for you. Right? That's the kind of have.
In their requirement and get it done. What is the use of their development? Or requirement?
That requirement they can set it, but still how much the Qualcomm will understand, because they have general purpose
System level knowledge
level
to develop
definition.
application.
And nobody will share the entire system to the third party, right? Then the Qualcomm will do the phones. Why will they use Snapdragon and then Apple doing phone, right?
So it is that system knowledge.
Application specific, yeah. Optimization can be done by the actual provider, solution provider.
Setting up a fab factory is nothing to compare to knowledge.
Yeah, very true.
Even online, if they want to ask a question, please unmute yourself.
Share my Gmail
Right.
if they have questions, they can
Right.
ask me.
Yeah, so I guess we'll wrap it
Yeah.
for today. And would like to thank Dr. Veena.
Thank you.
Thank you for the great talk.
Best. If you have enjoyed the talk.